students, welcome to the course Bioprocess Engineering. In previous class, we have discussed in detail the importance of various elements and nutrients that supports the growth of organisms. Also, we have discussed in detail the different methods that are used to optimize the growth medium to maximize the yield of given bioprocess. Can we imagine our life on Earth without oxygen? Yes, it is impossible. Oxygen is the gas that we breathe in to regulate all the activities. And what happens if oxygen is not present? Yes, our cells require oxygen in order to carry out all the metabolic activities and to produce the energy required. Similarly, all the aerobic organisms requires oxygen to regulate metabolic activities. Here, a fish tank is shown where we are able to see some gas bubbles that is coming up. Yes, it is nothing but the external air that is being fed into the tank through some mechanism. The air that is in the gas phase, once it is being fed into the liquid phase, it will be taking some time to attain the equilibrium state wherein the gases will be slowly getting dissolved into the water, and this dissolved oxygen will be readily utilized by the fishes to grow. Wherein a bioreactor is a vessel where the gas is passed into the reactor so that the oxygen that is present in the air will be readily utilized by the organisms, and this oxygen that is being fed into the reactor will be taking some time to get dissolved and be readily available in the reactor, and it is mandated to estimate the dissolved oxygen concentration in the reactor so that optimum concentration of oxygen will be available in the reactor for the organisms to grow. And as oxygen is one of the limiting elements supporting the growth of organisms, it is mandated to estimate the overall mass transfer coefficient of oxygen through the bioprocess. Hence, in today's class, we will be discussing in detail the different methods that are being used to estimate the overall mass transfer coefficient of oxygen in a given reactor.
Mass transfer is the net movement of a component in a mixture from one location to another location where the component exists at a different concentration. Mass transfer takes place between two phases across an interface. Absorption by a liquid of a solute from a gas involves mass transfer of this solute through the gas to the gas-liquid interface, across the interface and into the liquid. Mass transfer models are used to describe processes such as the passage of a species through a gas to the outer surface of a porous absorbent particles and into the pore of the adsorbent, where the species is adsorbed on the porous surface. Mass transfer is also the selective permeation through a non-porous polymeric material of a component of a mixture. Mass transfer operations in bioprocessing may be studied under following main categories: diffusional or convective mass transfer, liquid-liquid extraction, and mass transfer with phase change. In today's class, we will be studying in detail about diffusional and convectional mass transfer, whereas liquid-liquid extraction and mass transfer with phase change are the two techniques which are applied for purification of biomolecules, and these two topics will be studied in a separate paper downstream. The metabolic oxygen demand in a given reactor depends upon the biochemical nature of the cell and cultivation conditions. The dissolved oxygen concentration in a given reactor should be about 1 mg per liter. Oxygen consumption rate decreases with concomitant decrease in biochemical energy production. A critical oxygen concentration has to be met inside a reactor to facilitate all the metabolic activities. If the oxygen concentration inside the reactor is less than the critical oxygen concentration, The organisms starve for oxygen and cannot be metabolically active. The critical oxygen concentration for certain organisms are given here. For example, for E. coli, the critical oxygen concentration to be met inside the reactor is 0.26 mg per liter, and for Saccharomyces cerevisiae it is 0.13 mg per liter, and for Penicillium species it is 0.78 mg per liter. The temperatures mentioned here 37, 30 and 24 are the optimum temperatures that has to be met inside the reactor for regulating metabolic activities of the cell, and we can observe that the yeast requires a less oxygen concentration than E. coli cells, whereas the Penicillium species requires more oxygen to be. In molecular diffusion, mass transfer takes place purely by concentration gradients. That is, the molecules from the higher concentration region will move to the lower concentration region and try to equilibrate the concentrations in both the regions. If the two regions are in different phases and are separated by a boundary layer, diffusion takes place through the boundary layer. If the solute in the lower concentration region is constantly depleted by consumption of microorganisms, then the concentration difference exists and the diffusion continues to take place. This is known as continuous molecular diffusion process. This phenomena is known as continuous molecular diffusion process, and it takes place only because of the concentration difference. Any amount of agitation given to the system by means of stirring or gas purging will help us to equilibrate the concentration difference within the bulk of single phase. But the resistance to mass transfer lies mostly in the liquid side. The boundary generally does not offer any resistance for mass transfer. The mass flux Ja is given by dividing the mass flow rate by cross-sectional area. Thus, Ja equal to Na dash by A, which is equal to minus Dab into dCA by dy, where Dab is the diffusion coefficient of component A into the bulk of B and is given in meter square per second. Y is the distance measured from lower concentration zone to higher concentration zone. That is, the direction of Y is opposite to the direction of mass flow rate. This equation is known as Fick's first law of diffusion. Various theories have been proposed from time to time to predict the performance of mass transfer by diffusion. They are film theory, penetration theory, and surface renewal theory. Film theory is the most classical theory among them. It proposes the concept that a stagnant film of constant thickness, as denoted as del, exists between the phases at the interface boundary. Generally, there will not exist any concentration gradient within the phase, since it can be equilibrated by agitation. But, however, vigorous the agitation may be, the diffusional film exists, which in fact offers resistance for the mass transfer to take place. In this film, the mass transfer takes place solely by diffusion. The penetration theory is based on transient mass transfer. This model proposes that every element of the liquid surface is exposed to the gas for the same time period, theta, before it is replaced by the bulk liquid. During the time of exposure, the liquid element absorbs the gas as if it was a stagnant film and infinitely deep. The mass transfer is an unsteady state process, and the concentration profiles of the solute changes not only with distance but also with time. The rate of change of solute in the liquid will be changing and is represented by Fick's second law of diffusion, wherein Kl is equal to 2 into square root of dAb by pi theta, or square root of 4 into dAb by pi into theta, where theta is the time taken by a single bubble to travel a distance equal to its own diameter in the bulk liquid and is given by dB by UB. Thus, the penetration model predicts that KL varies at half power of DAB, unlike the predicted by film theory as where KL is directly proportional to DAB. The penetration theory was further refined by introducing the concept that the surface renews at every fixed interval of time. Thus, according to this model, KL is equal to square root of DAB into S, where S is the fraction of area of surface which is replaced with fresh fluid in a unit time and will have a units of second inverse. The surface renewal theory also predicts the dependence of KL on the half power of DAB, which is similar to the penetration model as a barrier for the molecular oxygen to enter into the cytoplasm of the cell. The gas bubble has to cross the thick cell wall of the bacteria and the fungal cells to be readily available for regulating various metabolic activities of the cell. The gas molecule has to cross the boundary that exists on the gas side and the liquid side as the molecules pass. As the molecules pass the interface, the partial pressure and concentration decreases, and after crossing the liquid flame, the gas will be traveling in the liquid broth to reach the cell aggregate. Similar to the liquid flame, on the gas bubble side, a liquid flame coexists along the cell aggregates. Various steps involved in the transport of gas from gas bubble to the bulk liquid and to the active site in the cell cluster is given here. There are about 8 steps involved. The gaseous component has to overcome these barriers before it reaches the active site in the cell or in the cell cluster for biochemical reaction to take place. Some of them are limiting and some are not. Step 1 is the transport of gaseous component, that is oxygen, from the bulk gas to the gas liquid interface. Step 2 is the crossing the gas liquid interface. Step 3 is the diffusion of gaseous component through the relatively stagnant liquid film into the well mixed bulk liquid. Step 4 is the transport of gaseous component through the relatively well mixed bulk liquid. Step 5 is the diffusion of the gaseous component through the relatively stagnant liquid film surrounding the liquid solid interface. Step 6 is the transport of gaseous component through the liquid solid interface. And step 7 is the diffusion of gaseous component within the internals of the cell cluster. And step 8 is the transport within the cell to reach the active site for the biochemical reaction to take place, wherein the resistance for mass transfer is negligible at step 2, step 4 and step 6, whereas the step 7 is the rate limiting step where the internal mass transfer resistance is significant, whereas the step 3 and step 7 are rate limiting steps where the internal mass transfer resistance is significant. Shortly, the oxygen molecule has to travel in the bubble form in the liquid phase and cross the solid layer. The three stages that the oxygen molecule, the transfer of oxygen from air to the cell are: first step is the transfer of oxygen from an air bubble into solution. Second step is the transfer of dissolved oxygen through the fermentation medium to the microbial cell, and the third step is the uptake of dissolved oxygen by the cell. The transport of oxygen through the gas and the liquid film are equal at the steady state. At the interface, the equilibrium between the liquid and the gas phase oxygen is reached, wherein the concentration of oxygen at the gas interface is equal to concentration is equal to its concentration at the liquid interface. The rate of oxygen transfer from air bubble to the liquid phase may be described by the equation dCl by dt is equal to KLa into C star minus Cl, where Cl is the concentration of dissolved oxygen in the fermentation broth. T is the time in hours. dCl by dt is the change in concentration over a time period, that is the oxygen transfer rate. Kl is the mass transfer coefficient and A is the interfacial area per liquid volume, and C star is the saturated dissolved oxygen concentration in the reactor. Larger the KLa, the higher the aeration capacity of the system. Design and operating conditions of the fermenter plays a major role in maintaining the overall mass transfer coefficient in a reactor. Dissolved oxygen concentration in turn reflects the balance between the supply of dissolved oxygen by the fermenter and the oxygen demand of the organism. If the KLa of the fermenter is such that the oxygen demand of the organism cannot be met, the dissolved oxygen concentration will decrease below the critical level. If the KLa is such that the oxygen demand of the organisms can be easily met, the dissolved oxygen concentration will be greater than critical concentration and may be as high as 70 to 80% of the saturation level. Hence, it is necessary to determine the overall mass transfer coefficient in a reactor. The overall mass transfer coefficient in a bioreactor has to be determined to study the aeration efficiency and to quantify the effects of operating variables on oxygen supply. Various methods are used to estimate overall mass transfer coefficient in a reactor. These methods are broadly classified as physical, chemical, and biological methods. The physical methods commonly uses the dynamic method, and sulfate oxidation, absorption of carbon dioxide, and dynamic measure of pH constitutes the chemical method, and biological dynamic gassing out, biological dynamic method with high oxygen uptake rate, and gas phase analysis forms the biological methods to determine overall mass transfer coefficient in a reactor. Static method of measuring KLa is based on oxygen balancing in the gas-liquid contactor and making use of the basic mass transfer equation Na is equal to KLa into C star Al minus Cal, in which Na is the total quantity of gas absorbed by the system per unit time and per unit volume. Thus, Na is equal to Vg into Cag of inlet minus Vg into Cag of outlet whole divided by volume of the liquid, where Cag is the concentration of the gas in the gas stream with flow rate of Vg. Thus, Vg into Cag of in gives the quantity of the gas entering per unit time, while Vg into Cag out indicates that in the outlet stream per unit time. The numerator indicates the quantity of gas absorbed in unit time. Combining the above two equations gives KLa is equal to rate of absorption of gas by C star Al minus Cal. In the above equation, Cag can be replaced by Pag by RT, wherein Pag is the partial pressure of the gas in the gas stream and R is the universal gas constant and T is the temperature. The mass flux equation can be rewritten as Na is equal to 1 by R into Vg into Pag by T at inlet stream minus Vg into Pag by T at the outlet stream. The oxygen electrodes are used for measuring CAL, wherein these oxygen electrodes should give accurate results. Otherwise, measurements of KLa may go wrong and give erroneous results. Except for this drawback, this method is simple and most reliable and can also be used when the fermenter is in operation. The dynamic method is an unsteady state process. Initially, the fermentation broth is made bereft of oxygen by stopping the supply of oxygen. Whatever oxygen is available in the system is consumed by the microorganisms. Thus, the concentration of oxygen reaches the lowest value at point P. Later, the oxygen supply is restarted to the system at a constant flow rate of air. Now, the oxygen concentration starts building up and the concentration profile takes the shape of PQ. If the air supply is more than the consumption by the cells, the oxygen concentration builds up and reaches a constant stagnant value of C bar AL. In the PQ zone, we can choose 2 points or and S at time T1 and T2, having the oxygen concentrations at CaL1 and CaL2. The rate of change of concentration of oxygen in the PQ region is given by the CaL by dt is equal to KL into A into C bar AL minus CAL, which upon integration yields KLA is equal to ln of C bar AL minus CAL1 whole divided by C bar AL minus CAL2 whole divided by T2 minus T1. Thus, KLA can be measured experimentally by measuring CAL1, CAL2, T1 and T2 by the application of the above equation. This is based on 2 points. For achieving better accuracy, we can collect a set of data points of CAL and T. They can be plotted on the graph taking ln of C bar AL minus CAL1 divided by C bar AL minus CAL2 on y-axis and T2 minus T1 on x-axis. The slope of the straight line passing through the origin gives an average value of KLA. This method is ideal for measuring KLA in an experimental fermenter, provided the oxygen electrode measuring the oxygen concentration can respond quickly to the changes in oxygen concentration. Normally, the time required to reach this saturation oxygen concentration, that is C bar AL, is only of the order of few seconds. The oxygen electrode has to cope up with the quick response. This is one of the oldest method and referred to as chemical method. The method is based on the chemical oxidation of sodium sulfate to sulfate by the dissolved oxygen in the presence of copper or cobalt as catalyst. In this method, the sodium sulfate is oxidized by sparging oxygen for a known concentration of time with agitation. The concentration of the sodium sulfate before the start of the reaction and at the end of the reaction is measured to find out the amount of sulfite oxidized. From this, we can know the amount of oxygen absorbed and consumed in the reaction. Usually, the oxygen is sparged for about 4 to 20 minutes. In this system, the chemical reaction is so fast that it is almost instantaneous. The concentration of oxygen in the system The concentration of oxygen in the liquid bulk is zero. Thus, CAl is approximately equal to 0 and the system is in mass transfer controlled one. Hence, the measured rate of reaction is actually the mass transfer rate from which KLa can be calculated. The sulfate oxidation method is mainly credited for its simplicity and ease of applicability. Its greatest utility lies in the fact that this method allows for characterizing the performance of the vessel under specified and reproducible condition. In today's class, we have discussed in detail the need for measuring overall mass transfer coefficient in a given bioreactor and also the various methods applied to estimate the overall mass transfer coefficient in the reactor. The reference books for today's content are Introduction to Biochemical Engineering by D.G. Rao, Biochemical Engineering Fundamentals by Bailey and Wallis, and the technical papers published by Tribe et al. And Dennis et al. Thank you.